So there's a helper document. We just, another master teacher and I kind of just drew it up just to make it easier. Not that you have to give it to your kids if you don't want to. Your kids could probably do it without it, but for us, it just shortened the amount of time they spent on the activity. Okay. And there are times where, you know, I'm like, let them struggle. They're going to get a lot out of it. They're going to learn. And this is one of those times, but you can bring that level up. You can bring a little scaffolding in for those students. Let me go ahead and open it and make sure it's where I think it is. Let me share my screen. All right. So we've got it. It's called 124 Sequential Logic Help Document. So this is not in the curriculum. This is just something we drew up separately. It could certainly be improved. You know, we kind of threw it together quickly like 7 years ago, and it worked well enough. So we haven't revised it. You know how those things go. You think about it the day before. You're like, oh yeah, well, all right. Here's this thing. It's still okay. But basically, you know, for kids who need it, here's like a photograph. Do this, right? We put the data sheet in there with some pins on it. If students were paying attention, when you show them how to do the footprint pin names, in theory, they don't need these, but hey, some of them won't, some of them will miss it, whatever. So this is another spot for them to see those pin numbers and what they represent. Okay. And basically in photograph form, it takes them through the entire first flip-flop, of which there are 4, right? It tells them how to wire one flip-flop, okay? And then it says, here's how you test it, okay? We're gonna test just this one flip-flop first. It should make a light turn on and off, a single LED on and off, okay? If it doesn't, we move on to the troubleshooting section, okay? And this gives some suggestions about how to troubleshoot and things to look out for, like little bent pins and stuff, if they have problems, okay? I don't often have kids automatically go to troubleshooting, except when they're not reading carefully and then they think this is also part of the build, and so they start doing this, and they're like, what am I supposed to do? And I'm like, well, I don't know, what are you doing? And they're like, I'm doing this. Does it work? I don't know. But that's a nice little section for them as well, okay? So if I haven't yet, I'll put this in the share drive too, so you guys have it. All right. So we're going to head on over to our random number generator. So I'm going to go back to our curriculum here. So this is 1, 2, 6. Now, it's actually 1, 2, 6 and 1, 2, 7. I'll explain why in a moment. So this is a really cool project to me, I think, because it's a really great combination of all the things we've learned so far. It's got some resistors in there and some LEDs. So you've got like kind of some series stuff in there. It has some very basic sequential logic, which is what we did in 1, 2, 4, which is like a counter. It has some very basic combinational logic, which is what we messed around with in 1, 1, 6 and 1, 2, 1, which is the gates, the AOI stuff. And so kids are still very much like kind of nebulous. I've seen these things, but I don't get them yet. I don't necessarily fully understand them, or even maybe a little understand them, but they've seen all these concepts. So this is now like the 3rd time that we're going to talk about AND gates and OR gates and inverters, and they're starting to get a taste for it now, okay? So here's what we need. And I think this is a really clever design, okay? And I talked through this a little bit last week, so maybe I'm repeating myself for a second. But this this random number generator is actually a really clever design, because it doesn't actually do random, because random is super difficult, okay? Let me turn off my green screen background here so you can see it. There we go. So random is really difficult in electronics. Electronics is really predictable, so random is really difficult. So this thing is not random really at all, okay? It counts from 1 to 6, that counts from 1 to 6, okay? And what it needs to do is it needs to give us the illusion of chance, or like sort of the reality of chance. I need to be able to have it select essentially a number from 1 to 6, because that's really all I need it for, right? This isn't being, used to, do random seeding for a lottery or something. This would be like if I'm playing Monopoly, okay? I need it to be random enough, right? Where if I press the button, I'm going to get a number between 1 and 6, and I don't really know what it's going to be. I can't predict it. I can't manipulate it. It's just going to land on a number. And that's really all I need. I don't need this to be truly random. I just need the element of chance. And so what we're going to do is we're going to have this thing. I tried to do this last time, but it didn't work out so well. Yeah, there we go. So what we're going to do is we're going to get this thing so that when I press the button, it can kind of roll through some numbers. Okay. It's being kind of weird with the switch being funky and with zoom. But ideally, all we have to do is have it go fast enough, right? So that I can't really tell what number it's going to land on. My soldering iron's still out. My brake, I'm going to solder it up so you can actually see what it does. Anyway, so if it runs through 1 through 6 fast, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, zooming through it, that would make it pretty difficult to land on the number I need, right? If I'm trying to get a 4 or something, it would make it pretty difficult to be like, well, wait, right? So that's the first step to making this thing kind of semi-pseudo random. But it can't go too fast because we'd actually like to see the numbers sort of blinking and twinkling and moving, because that makes it a little bit more fun. You can kind of see the dice rolling. If this went through the numbers so fast, crazy fast, these would all just appear solid. It would just look like all 7 were lit up, and then you'd let go and it'd be like 3, and it wouldn't be quite as much fun. We want to see it kind of blinkety, 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 and then land on a number. So we have to design our 555 timer circuit to be fast enough so I can't game the system. I can't let go when I want, and slow enough that I can still see it twinkling. So that's one of our engineering challenges, to pick a frequency that's in that good range. Okay. And then the last thing that this does, which I think is a really cool little thing, is they made it so when you let go of the button, it doesn't immediately stop. Okay. It kind of stop. It kind of rolls to a stop almost. Okay, which I think is pretty cool. It kind of gives the illusion and the sort of the fun of an actual die, like rolling, right? And plus that makes it even harder. Even if you were like the world's fastest finger here and you could be like, I want to stop right there, it's still gonna roll, stop when you let go. So it doesn't stop right when you take your finger off of it. So all of those things take from this design, which would be kind of lame, right? It's just a thing that goes from 1 to 6, and make it a lot more interesting, a lot more marketable product. And remember, we're engineers, right? We're trying to solve problems, but at the end of the day, for the most part, it's a product, right? We're trying to sell this thing. So what we're going to do in 126 and 127 is we're going to break out this design into its component parts and put them into multisim. Okay, this is basically the last discovery activity. After this, we start to dive really deep. So this is what you're going to look at in 126. This is what you're going to do. You're going to create this circuit here, and actually, I'm going to bring up the PowerPoint because the PowerPoint on this is pretty decent. You're going to build this circuit in multisim, but it's essentially the 555 timer you've already built 4 times now. You built it in 116 without knowing what the heck you were doing. All right. And then in 125, which was the most recent activity, we messed with a little bit more, changed our A and R, B, and C, kind of saw what that did, looked at the equations and the expressions and such. What the heck is going on? Sorry. Awesome. You think you're all cool because you have matching monitors with the same brand and everything, but then you don't know which one is actually which when you're trying to display them for your participants. All right. Can you guys see that slideshow? Yeah. Okay, great. All right. So they give us this block diagram. Block diagrams is the first time kids are seeing a block diagram, and it's important to maybe stop and talk about it for a minute, because block diagrams are so helpful, because often you don't really know how to do the entire circuit off the top of your head, right? A lot of times we'll represent with just a rectangle and say, okay, this is what needs to happen in this rectangle, and I'm going to figure it out later. I'm going to dive in and figure out that chunk later. Or maybe I split it up into different teams. Maybe this engineer works on this block and this team works on this block, and whatever the case may be. So here we have a block diagram, and we say right here in this rectangle, we need to generate a wave. We need to make a wave that goes up and down. Well, that's the job of the 555 timer. We messed with that already. We know we can do that. We know how to make a wave. That's cool. But the other thing about that is we have to make that dampened wave, meaning a wave that slows down. Because remember, when we let off that button, we want to go and stop, right? So it's a little bit more of a challenge. We've been making waves. We know how to make those, but we need to make this damped wave. So they're going to help us through that. So this is what we're going to talk about in 126. And then right after that, we're going to talk about this in 127. So we take this wave and we use it to count. We're going to use it to count from 1 to 6 in binary. So 001, 010, 011, 100, counting in binary. So whatever happens in this rectangle, it's going to take my clock pulse and it's going to turn it into a count. And then finally, this is the other part of 127. It's going to take this, in this rectangle over here, it's going to take this binary number and it's going to tell these LEDs how they should light up in order to represent that number. For example, if you have a binary 1, just this center LED should light up. If you have a binary 4, the 4 corners should light up. So in this little rectangle right here is some logic that tells those lights when they're supposed to come on. So a lot of challenges here for us. Luckily, they're going to scaffold us and help us out a ton through this activity. Okay, so we're going to focus on the analog section. So this is the circuit. Ta-da, it's done. Thanks, great. Okay, now what you'll notice, what you may notice, if I can annotate here for a second, is from about here to here, that's the circuit that you have done many a time. Okay, that's a regular 555 timer circuit. Okay, we got RA, RB, and C. Here's that buffer capacitor that Ralph struggled with right there. So this is a regular 555 timer circuit. The difference is what they added up here. This I think is super clever. I didn't invent this. I wish I did, because it's such a cool idea. And so what they did is they put a big old capacitor in here in parallel. See, it's in parallel with my RA, RB, and C. So when you press the button down, it's rolling, it's rolling, it's rolling, it's rolling. That's great. Okay. And everything is normal. But meanwhile, that's happening. This capacitor over here is charging up. It's filling. It's filling up, it's filling up, it's filling up, it's filling up, it's filling up. It doesn't really affect the rest of the circuit because it's in parallel. It's just happily, quietly filling up over here to the side. Eventually, it fills completely up and fine. Then it just sits there full. It doesn't blow up or anything. It just sits there fine, 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 fine. Okay? And the circuit will run like that forever and ever and ever until somebody takes their finger off the button. Okay? So here's the button right there. Okay? When someone lets go, what's going to happen? Well, what would normally happen if you let, all of a sudden this is disconnected from 5 volts. So this whole thing would just stop working immediately. Stop. Okay, it no longer has 5 volts into RA. This thing's just going to stop working. But this capacitor now is called into action. The capacitor goes, ooh, I've got charge. You're going to let me empty this charge? Absolutely. So now this capacitor starts spilling back into the circuit and keeps it running. So even though I've disconnected from power up here, this capacitor is acting like kind of a full battery. spilling charge into this, and all of a sudden this is still counting. Count, 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 count. Great. So it still gets to count even though I let go of the button, which is awesome, except a capacitor has a limited charge, right? It's a bucket and it's kind of full, but you're going to empty it. So as this charge empties, the voltage starts to drop and drop and drop and drop. And what happens here is my count, because the voltage is dropping, gets slower and slower and slower and slower until finally it doesn't have enough voltage to roll anymore. It stops. So it's just a clever design, I think. I think it's pretty clever. Okay. Now, they're going to tell you, let me stop annotating here. They're going to tell you here that when you make it in multisim, let me get there. Oh, where is it? What the heck? Must be in the activity. They say when you do it in multisim, they tell you don't put 100 microfarad capacitor here because multisim is going to simulate really slowly. And, you know, we all have things to do. So they say, go ahead and put a 50 microfarad capacitor in here in multisim, just because you don't want to sit there and wait all day for this thing to charge up and then discharge. So that's the first thing they suggest. And then they also suggest this push button. Come on. This push button here in multisim is kind of difficult to like click and hold. So they say, go ahead and put a switch in instead, like a single pull, single throw, or a single pull, double throw switch. So you can click it closed and click it open. So they're just telling you that. All right. Here they're showing you on the oscilloscope what happens. When I hold the button down, there's my square wave happily clicking along. Nice regular period and frequency there. And then you let go. The capacitor, this bottom one, this capacitor starts to empty, 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 empty. And my wave starts to spread out, spread out, spread out, spread out, spread out, until it gets to about here. This voltage drops below, I think, 3.7 volts or something like that. Maybe 2.7 volts, whatever it was. And then it can't count anymore. We're done. Okay. So in the activity, they're going to ask you to measure, break out your oscilloscope and measure the frequency way in the beginning, somewhere in the middle, and somewhere at the end. This is tightly zoomed in, this right here. You're going to measure it over here in the beginning, over here in the middle, over here at the end. Okay. So you'll build that in multisim, basically monkey see, monkey do. Build this. Okay, great. One thing my kids do often, and my participants do too, is they start searching for 555 timers and they find like other ones that don't work. Use this part number, LM555CN. It simulates correctly. Use that one. People grab 555 timer rated. It does not work. Okay, so grab this one, LM555CN. Okay, so that's my first portion. I had a 555 timer to make a wave, just like we did before, but then we added this resistor, this capacitor, and this switch so that it slows down before it stops. Questions so far? And again, you're not looking for, I mean, I know you want this, but with your students, you're not looking for necessarily like 100% understanding, although at this point, 1 to 5 prepped them pretty well for this, so they should be like, okay, like kind of okay with what we're doing here. They may not have been able to design it on their own, which is totally fine, but maybe understanding why it's doing what it's doing. So that's 1 to 6. So I would lecture on that, and then give them a day to build that in multisim, typically, and measure it. And then we would go on to 1 to 7. 1 to 7 is another PowerPoint. If it was me, I probably would have put them all in one, but it works better to lecture it this way anyway. lecture analog, have them build analog, then lecture digital and have them build digital, I think. Enable editing. So now we've got our wave. First part's done. Now we're on the second two blocks. How do we do that? How do we get it to count? And how do we get it to display on the die as though that's what it was? Okay. Man, PowerPoint is chugging. When I run Zoom and a Power Mirror and Multisim and PowerPoint and 10 tabs in Chrome, it's struggling. Can't imagine why. Okay, cool. So now we've got our clock. Now we're dealing with these. So this is our center rectangle is what we're going to talk about first. So this center area might look a little familiar. I'm not going to say super familiar because they've built it one time essentially. They did one flip-flop in 1.1.6, and then they just did it in 1.2.4. They built a bunch of these flip-flops together. But okay, you pointed out to them, hey, you just did this as your last activity in 1.2.4, just a reminder. So we've got D connected to Q naught, just like we did in the other circuits. We've got our presets, you know, kind of tied up. We got the clock tied to Q naught, just like we did before. So we've built this thing at least before, kind of. But here's the thing. Here's another little modification we have to make. Because if you have 3 flip-flops, you can count from 0, 0, 0, which is 0, to 1, 1, 1, which is 7. So if I do nothing else, if I just throw these 3 flip-flops up here, I have a 0 to 7 counter. I do not want a 0 to 7 counter. What do I want for my die? One to 6, right? 1 is the 6-sided die. It's supposed to be 1 to 6. So that's what I really want. I really want 1 to 6. And so we are going to dive into this deep, and you will get more than you want on this. But right now, you're going to have to take my word for it that this circuit in the bottom right corner is what is limiting that count. This tells it to start at 1, and it tells it to reset after 6. I promise almost all of Unit 3 is about this. Okay, we are going to spend weeks on this. So right now, you don't have to dive too deep. Just know that this here tells my counter to start at 1 and reset after 6, which is what we're looking for. Okay? So cool. So then we brought in our clock signal from our previous activity. We're counting from 1 to 6. That's cool. And then they're leaving this block. They're going to the next block. Here they are. There is a long explanation about how this is happening with colors. You can walk through each state if you like. And now we're going to get into this last rectangle, this combinational logic section. Okay, so this is going to take a binary number and tell it which LEDs to light up. And this is what that looks like. Again, they're given the whole circuit. Here, just build this thing. Okay. And this is neat. I never even realized this until I did this activity. They point out that some of the LEDs, some of the dots are always on together. Okay. For example, L1 and L5, these two corners are always on at the same time. And I was like, oh yeah, I guess so. Like 2 they're on, and 6 they're on, and 5 and 4, yeah, they're always on together. So instead of building 2 identical circuits, they just took the wire off of this one and brought it down here. Very efficient, right? Great. Same thing with L2 and L6. They're always on together, so they just wired them to the same circuit output. And also L3 and L7. So instead of having 7 circuits here, I have 1, 2, 3, 4. So that's way better. I saved a ton of chips there. That's awesome. All right. So, question? Nope. Yes? Got my hopes up. That was the equivalent in class when like a kid stretches and you're like, yes. And they're like, no, I was just stretching. Like, oh, dang. So I'm going to put a binary number from 1 to 6 in here. My counter is happily counting and it's giving me numbers. So maybe it's 1. So it'd be like 0, 0, 1. This circuit right here would say, okay, 0, 0, 1, L4 should be on and everything else should be off. That's the job of this circuit. Now when it gets a 2, so 0, 1, 0, it's going to say, oh, okay, so L1 and L5, I think. It might be L3 and L7. I don't remember which corner is which. But L1 and L5, those should be on. Everything else should be off, for example. Okay, that's this circuit's job. So they show us a little truth table here. They say, all right, so here's, there are 3 inputs. We're going to talk about truth tables here in just a moment. There are 3 inputs. This is on my counting from 0 to 7. Okay. And when I have a 1, when I have a 1, which is this row right here, what should be happening? Well, L1 and 2 and 3 and 5 and 6 and 7 should be off. So we give them a 0. And L4 should be on. So we give it a 1. That's what this looks like. Here I have a 2. So L3 and L7 should be on. And everything else should be off. Here, this is supposed to be a 3. So L1, L4, and L4 and L5 are on, and everything else is off. So that's how they went through and did this. Now you'll notice, Jim and I were having a conversation about this yesterday, that 0 and 7 are not filled out here. Why not? Well, I mean, I would think 0 would be 0, 0, 0, 0, 0, 0, 0, and 7 would be 1, 1, 1, 1, 1, 1, 1. Why didn't they fill them out? Any guesses? I know Jim already knows, but why wouldn't they fill those out?
Because we don't use 0 or 7.
Yeah, we don't care. At this point in the circuit, there should be no way of having a 0 or a 7 because our previous counter in our previous block limited us 1 to 6. So it's never going to see 0 and it's never going to see 7. So I don't care. Well, why not just put it in there? Well, because it would cost us more logic to make sure that this displays a 0 and to make sure that this displays a 7. It would take more logic to do that, and we don't need it, right? That's wasted cost, wasted battery life, wasted power draw. Those don't care conditions are pretty darn helpful. I'll tell my students about, like, if you're traveling upwards in an elevator and you hit the door open button, it does not care. It doesn't care if that button's pressed or not. It's not opening the door, right? While you're moving. So we use those conditions all the time in digital electronics to simplify circuits. I don't care what's happening in this scenario based on this other condition. Okay. Now, oddly, you'll find this when you do the circuit. When you're at 7, it actually does light up all the LEDs, and that's totally by accident. It's totally coincidence that does that. So the kids are really confused. They're like, well, I put in a 7 and it shows a 7. Great. Okay. However, in this row, I believe it displays a 2 or something. Okay. It does not display a 0 because we never designed it to. And it's just coincidence what happens. So I think here it displays a 2 and you'll be like, well, why does it display a 2? Because we don't care. That's a situation that we're never going to see. Okay. And then they go through, again, you know, how each thing is lighting up. Again, you know, I'm going through this pretty quickly with you guys, and I don't think you need to go through these things in great depth because I don't feel like the students are super ready for it yet. We're still sort of in the, this is kind of why this is happening, build it, okay, cool. The next thing we're going to do, right here, we're going to close out unit 1 and go to unit 2. Now we're going to dive into this deep. Why does this do what it does? Why does it build? Why did we build it this way? And by 2 weeks from here, in the real curriculum, in real life, they'll be able to build this kind of circuit no problem. I mean, easy. So going through it at depth here, I think is not really necessary. Okay. And then the last thing, they just kind of remind us that probes are make-believe fantasy land. Those are not real things. Those are just simulation things. So in real life, we'd have to put an LED and a current limiting resistor and run it to ground. So that's what we'd have to do if we were actually going to build this thing, which, you know, we are. Okay. And so now they put it together. Now this drives me nuts. I guess because they couldn't fit on the slide, but to me, it's incredibly unsatisfying to not have the whole circuit on one slide so I can look at it, right? I'd love to see the whole thing in one. So I require my students, both my high school students and you guys, to put all this thing in one multisim document so you can actually run it, right? You can press the button, watch it blink and blink and blink and blink, let go of the button, have it roll to a stop, and then display a number. You want to see the whole thing, right? You want to see the whole thing work, of course. And so I think that's actually the submission for this, is that whole circuit together in multisim. Okay. So yeah, they have you build them separate, but please don't hesitate to copy paste. Once you have it built, copy that chunk into another document. Don't literally rebuild the whole thing. Just copy paste. We're not breadboarding this, which is really the only time I caution against copy paste. We're not putting on this on a breadboard, so copy paste to your heart's content. Okay. Questions on 126 and 127. I mentioned last week that there's nothing wrong with waiting to solder until after this, if that's how things work because of COVID or because of your ordering or your budget or who knows what. To me, it works just as well if you do it earlier or if you do it after this. It's just all on how you deliver it, right? Either you're talking about this thing that we made when you reference 124 and 125 and 126, 127, or you do all that stuff and you say, now we get to make this cool thing with these concepts that we learned in 126, 127. So about the same. All right. No Tinkercad on that, by the way. This is all in Multisim. You can do it in Multisim Live. I think, I don't know if you guys saw it. Of course, I stopped sharing. They do have a Multisim Live option for this. They tell you you can go ahead and use Multisim Live to build these things up. Here they give you a little peek of what it would look like in Multisim Live. So it's pretty similar. I mean, it looks a little bit different, but not much. Instead of using VCC, we use a battery connector. So like, it's pretty darn straightforward there. So same thing down here. You can actually see the counter. Okay. All right. Awesome. So that, my friends, brings us to the end of Unit 1. Done. Quit. Originally, that was planned to be a 9-week unit. It was supposed to be a quarter. I think it's in your best interest to try and get through it a little bit faster if you can. I know this year is bizarre, and I can't tell you anything about schedules this year, but on a regular schedule, I would say you'd want to get through that typically in about 6 weeks, unless you're block schedule weirdness, which, you know, I don't know how you guys run your life, but on a standard schedule, I'd want to get done with that before the end of first quarter, probably 2 weeks before the end of first quarter, so I could start Unit 2. Unit 2, to me, takes more than 9 weeks. It was designed to be a quarter, but I think it spills out. So you want a little bit more time to work on Unit 2.
I do have a question, Mike.
Please.
So Multisim and Multisim Live, I think the live one is easier to install. I think I have some students who are having problems with the Multisim, so I'm trying to figure out which one to tell them to do. Maybe the limitation with the laptop they have is, so should I just tell them to do the Multisim Live and just go with that one, or just, what's the difference in terms of features?
Sure. So Multisim Live is significantly less featured. However, because we don't need a tremendous amount of sophistication, we can do a good portion of the curriculum with Multisim Live if we need to. As you stated, yeah, it could be They could have a Chromebook, they could have a Mac, they could maybe not meet the specifications. There's lots of reasons why Multisim may not work. It's not like Inventor or 3D Studio Max or something where it's like a huge lift hardware-wise, but sure, there are reasons why it might not work. So for compatibility's sake, Multisim Live runs on pretty much any browser.
Mhm.
It actually works fairly well on the iPad, as well as you might expect on the
Right.
iPad. If you're looking for maximum compatibility, I'd say Multisim Live is a good choice. There are going to be a couple of activities where we can't do it in Multisim Live, and that's actually laid
Mhm.
out in the distance learning thing. It just says, you know what, don't bother because you can't do it. For example, multiplexers and demultiplexers. There's one activity that we do on Mux and Demux, and they just don't exist in Multisim Live. So you just say, okay, well, you skip it or whatever. You can't do this in Multisim Live. So
Right. Okay. Thank you, Mike.
you're welcome. Okay, so let's see. We're a little early for a break, but I think it actually makes sense because we're about to jump into Unit 2, so big mental shift change. So why don't we go ahead and take our break just a few minutes early here. I got about 7:49. So let's go like 5 after. Excuse me. So that would be, no, that would be too long. 55. 55. We'll reconvene at 55. All right, folks, let's get right back to it. So this is exciting. The Unit 1 is, it's review for some of the kids. It's analog electronics. It's fine, and some people like circuit analysis. I like circuit analysis. But really, that's not what the kids signed up for, right? It's not really digital electronics. And Unit 2 is when we actually start with the digital electronics proper. And I think it's really the most fun part of the entire course, really, is like 211 to 216. That's really where the power of the course is. They're going to make such huge leaps forward in sophistication of what they can do in a couple of weeks' time, which I think is really neat. What I like to do when teaching this course is, and I mentioned this before, I like to introduce the project first, and then we'll build our skill to get to that project, right? So the project itself is sort of this carrot, right? This little intrinsic motivation to be like, ooh, I want to do that interesting thing. So how do I build the skill to get there, right? And so to that end, we're going to talk about project 216 right now, okay? So 216 is a project, all right? It's not a problem, but it's a project. And so a project is sort of in between. Remember, activities are very well scaffolded. Here's everything you need. We're teaching how to build a skill. And a problem is really poorly defined, lots of possible answers, could be really whatever. And the project lies in between. So the project is still scaffolded, but there's generally one right answer. And you're going to help them kind of get to it and design and build that thing. So we are going to talk about 216, majority vote. That's kind of our first project that we're going to do. Now, together right now, we are all going to work on the design brief for 216. And this is something that you're going to have to turn in as a submission. And so we'll all just kind of knock it through here together. It is worth at your school. I don't know what your situation is. I don't know what kids have to take before they take this class. But if they've had engineer's notebook training, they took ES or IED or POE or any of those classes, they should have been trained on how to write an engineer's notebook. And it might be in your best interest to check in with those teachers to figure out what format they've taught them, so that you can stay consistent with the kids. Okay, the format's not like wildly important if you vary or whatever, but that consistency is probably a good thing. I mean, if you're the IED teacher or POE teacher, it's even easier for you. But I would check in. So I'm going to use my format today. You don't have to use my format if you have a format that you prefer, that you'd rather use. I don't care, but I'm just going to do mine, and you're going to do one as well, whether it's my format or somebody else's format. So the first thing I would start with at the very tip top is my title. Okay, and when I'm doing this with my students, I would do this on the whiteboard, and everybody's following along with me, right? them writing it out or typing it out if they can't write for whatever reason is way better at kind of solidifying this. So we're writing this in the engineer's notebook. Title. This is going to be called Majority
I'm not seeing anything, Michael.
no, you're probably not, because I didn't share it. Thank you, Wayne. You're the best. Can you see it now? Yes?
Yes, yes.
Awesome. Awesome. So my title is Majority Vote. I am not in an engineer's notebook. As you can tell, I'm in loose leaf paper here, but this would be in the engineer's notebook if you're going to do that with them or whatever. So first is title. Next, typically client. And you can generally do whatever you want there. I'm just going to kind of put generically board of directors. If you have companies that are on your advisory board or you have connections to industry, local industry in your area, local engineering firms, you can always put them down here, kind of give the kids a tie to it. Then we do designer or designers, whichever the case may be. So you'd put your name there. Don't put my name. You'd put your name. Okay. And then some people do a problem statement and a design statement. I'm just going to do a straight up design statement. I'm going to go right there. The difference being that a problem statement defines the problem and a design statement basically says what you're going to do to solve that problem. So at this point I would stop and I'd talk to the kids about what this circuit is. Right now you just have this piece of this like very limited pieces of information. And what does this circuit need to do? Okay, so let's stop and chat about it for a minute. So when you read the actual lead in for 216, it talks about the 2000 presidential election. And those of us who were around for that, there was, you know, some voting issues in Florida and whether or not votes got counted because the paper wasn't all the way punched through and blah, 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 blah. And it was an incredibly close race in some of the counties in Florida. And so it was a big deal, which is true. All of that is true. But it actually has very little to do with what we want to build here in 216. So I don't actually love that lead in because it's like talking about a presidential election, but that's not what we're building here. Okay. What they want us to build here, what they want us to design is like a secret ballot system for a board of directors. Okay. So we have this board of directors. It's made up of 4 people, the president, the vice president, the secretary, and the treasurer of the board. So 4 people. And they're going to vote yes or no, yay or nay, on a motion that is presented to them, right? So we move that we're going to have bagels for lunch. Everybody votes yes or no. And then we don't know. It's a secret ballot, right? So we don't know who votes what, but I get an answer. The motion passed or it didn't. Okay? And as you may tell from the title, the majority wins. Okay? So the majority of people vote yes, the vote passes. The majority of people vote no, the vote fails. Okay? And I just want a little light. If the light lights up, the vote passes. If the light's off, the vote fails. That's what I'm going for. Now, some of you may pick up that there's a little bit of a problem here. What is the problem with a majority vote circuit if there are 4 people voting? I can have a tie, right? Okay, so I can have 2 and 2, and there's no majority. Okay, so that's okay. They've explained that to us. If there's a tie, whichever way the president voted, that's the way the motion goes. So if there's a tie and the president voted yes, the motion passes. If there's a tie and the president voted no, the motion fails. The president does not get to vote again. The president does not get the tiebreaker vote, right? And the president, it's not whichever way the president votes, it goes. It's not a dictatorship, right? The president can be outvoted. If the other 3 vote yes or no, then that's the way the motion goes, okay? So that's what we need. We need a circuit that we're going to vote with, kind of a secret ballot thing. It's going to tell me the outcome. And so now I need to come up with a design statement. Now, a design statement is usually a 1, maybe 2 sentence, concise description of what we're going to do, right? What we need to build here. And so I always begin mine with these 3 words. We're going to design, build, and test. Pretty much anytime I do a project in any one of my Lead the Way classes, that's how the design statement starts. Design, build, and test. Because we're pretty much always doing one of those things. I mean, maybe we're not going to build it, but what would be the point, right? So we're going to design, build, and test it. What? Design, build, and test what? So give me some thoughts out there in TV land. What do you think you would put after this? Design, build, and test what? You have to draw this out of your students. You have to tell them it's, we'll just workshop it. Nothing's permanent. So just give me some thoughts and we'll work it through together. What do you think? Design, build, and test.
A voting machine.
A voting machine. Okay. I like it. We'll start with that. A voting machine. Okay. How detailed do we get in here? Well, that has to use 74 series. No, we don't want to get too into the details here because we have a section coming up called constraints, and that's where we'll put like all that other little stuff in. But maybe I need like one other thing here. Design, build, and test a voting machine that what? What does it do?
Displays the winner by majority.
Okay. I like it. That displays well, it's not the winner, right? It's not a person. What would we say? Like
Say candidate.
Whether it passes or fails.
Right. It's about like a motion, right? It's about like should we do this? Should this law, whatever. So it's not like a person or a candidate. It's
You just say result.
Result. Sure. Sure. The result, the outcome, something like that. Result. Of a, I don't know, majority vote. I probably shouldn't have said voting twice, but that's okay. Of a board of directors vote, of a secret ballot, something like that. Okay. So we'd work through our design statement, kind of develop it out. Later on in the curriculum, I will expect students to just develop this on their own. But right now, we're all kind of doing it together, scaffolding. This is the format I'm looking for, et cetera. In the newer IED, they split out criteria and constraints. If anybody out there is an IED teacher familiar, they split them out. Okay, Skylar, and so they split them into criteria and constraints. And from what I understand, it's just sort of like a semantics thing a little bit that like, what's criteria? What's the difference between criteria and constraints, IED people, do you know?
I always tell my kids, your constraints are your limitations.
Yeah, your limitations, right, well said. Like it can't go more than this, right? You only have 3 of that, right? Whereas what's your criteria?
Criteria like comes from the board of directors saying, okay, this is what we want. It's more coming from the customer saying this is what it has to be.
Right, cool. So they split those up. I don't in my class, I just do constraints. But if you want to stick with that IED kind of consistency, you'll kind of split those into two different categories. It might be a good idea anyway, even though Crash doesn't do it, because in the newer EOCs and the end of course assessments, they've been spilling in more design process into some of those things. So you may be worth talking about. All right. So constraints, mostly this is provided by me, right? This is mostly, I'll just kind of give these to the kids because most of the time they're technical enough that they wouldn't just guess them, right? For example, must use 74 series chips, right? Like they wouldn't have guessed that. tell me about the vote. That should be in the constraint. How is the vote supposed to work? How do we describe the outcome of the vote?
Ties are broken by the president's vote.
Ties are broken by the president's vote. What happens normally?
Majority wins.
Okay, so I would say majority wins, and then right underneath that, ties are broken by president's vote. Sure. Okay. I'm going to put another one here that the kids won't understand, but they will when we're done. Must be in SOP form. And they're like, what's that? I'm like, we'll get there. Trust me. We'll get there. Today, in fact. Okay. And I think that's pretty much it for constraints. I always say, hey guys, if you think of any more, we can always circle back to this. If you come up with anything, you think I have any questions, we can circle back to it. For right now, we're going to move on to the last thing I put on here, which is deliverables. So the deliverables would be what your client is looking for. Typically, in this case, it's the teacher, right? What do I need from you? That's kind of your deliverables. So this is kind of a longer list. There's quite a few things in this list. So we're going to knock through this. So first thing on my deliverable list is the design brief. Hey, good news is we're almost done with that. The next thing is the truth table. And I like to put these, I'm basically putting these in chronological order, which I like. Okay. After truth table, we have unsimplified, logic, expression. Unsimplified logic expression. How do I want to write this? This next thing you participants in my cohort here are not going to do, but we have the students do it in class. So I'll put like a star here or something. Okay. Unsimplified circuit in multisim. This is the only time we have them deliberately build an unsimplified circuit. We do it just one time so they can compare how amazing it is when we do simplification. So we can really sell the point like, oh man, you want to do simplifications. Every point from here on out, which I think is really authentic, we're like, you should always find the simplest form, right? But this one time, we're going to make them do it. You guys aren't, though. You're not going to do the circuit multisim, that unsimplified one. All right, next up, we have Boolean, B-O-O-L-E-A-N, Boolean simplification. And then I'm going to write with theorems. Again, that'll make a whole lot more sense once we get into it. Next up is simplified expression. simplified circuit in Multisim. Two more things. Evidence of working prototype. That one statement covers a lot of ground, right? Because they have to prototype it, so they have to like build it, breadboard it out, right? They have to test it and prove that it works, and they have to deliver that evidence to me in some way. Most of my kids choose to record a video because they have to go through 16 states here when we get there. So as opposed to taking 16 pictures and trying to turn all of them in, typically they just record a video going through the states. But that's all in there. And then the last thing is a reflection. With the students, I have them, talk about what they've learned and everything else. And you can write a reflection from a student perspective if you like, about what did I learn as a student right now in this class. But you can also, if you prefer, to write that from a teacher perspective. What are you going to need to watch out for when you're teaching this to your kids? What do you think they're going to struggle with? How will you present it in a better way than Crash did? Any of that good stuff you can put here in reflection. That's fine. I don't mind if you write that from a teacher perspective either. So that's our big old design brief. Now it's a little overwhelming, partly because we don't know how to do this stuff here. There's words here that I don't even recognize. So we say, okay, cool. So now you're going to build the skill to be able to do this. Now, what I really like to do, and this isn't exactly how it's written in the curriculum, I like to kind of do my activities and this project in parallel, in tandem. So they're going to learn how to do a truth table, and then they're going to do a little activity on that. And then I say, now do the majority vote truth table. Now you know how to do it. You've got that skill. Now do it for majority vote. Cool. And then they're going to learn how to pull a logic expression. Great. Now go do it for majority vote. And then they're going to learn how to put it into multisim. Great. Now do that majority vote. And like always having this little project, this thing that they're working on, helps motivate them to figuring out how to do these skills, right? I need to figure out how to do that because I got to do it for majority vote. So it's authentic the whole time, which I think is really nice. Okay. Questions on design briefs? I'm at the end of my page on a engineer's notebook. I might cross off if there's any empty space down here, and then I would sign it. And I would date it. Today's August 25th, 2020. If I had someone nearby, I might have them witness it. They can write, sign it too. By the way, this is a good moment to mention a word from our sponsor, perhaps. On the purchasing manual, PLTW has actually really nice engineer's notebooks. They're pricey. I think they're like $3, $4 a piece or something. So they're expensive. I typically would tell kids to go to like Staples and get a sewn binding quad ruled notebook because they're about $1 typically at back to school time. But if you can spring for it, if you can put it in your budget, or you happen to be in a wealthy area where they don't bulk those sorts of things, the actual engineer's notebooks are super nice. They have page numbers done. They have areas where you can actually do, you can sign it and witness it and all that good stuff. They have a table of contents. They're really nice. So. All righty. So that's 216. That's the project. That's the goal. So we're going to roll now and we're going to learn some skills. We're going to go to 211, which is the very first activity in Unit 2. Okay. And it's called Truth Tables to Logic Expressions. So our design process, there's a little graphic here which is worth looking at. Let me just share it with you. Nope, that's not it, right?
All right. So we got.
There we go. So this is their, you know, we don't teach kids a whole new design process or anything. This is just sort of a little guide for how we are going to make these circuits, right? And so we start with a word problem. That's what I just did with you guys. We talked through the circuit we need to make. And so the next thing we're going to do is we're going to create a truth table. Okay. We're going to write our logic expression from that truth table. And then we're going to actually turn it into a circuit with AOI logic implementation. Word problem, truth table, expression, and then circuit. So that's what we're going to do first. Then we're going to learn that we can use Boolean simplification. This isn't today. This will be next time. How we can use Boolean simplification to make those things smaller and better. So this is kind of our first step. This is how we're going to do majority vote. Later on, we're going to add in extra goodies. These are not essentials. They're just handy shortcuts. More like ways we can simplify it more. We can get more efficiency out of things. We can eke more out of it. What's cool is that even at this stage, they can make real world, functional, efficient circuits, which is pretty awesome. Okay. So that's the very, very first PowerPoint they show, is just to give them an idea of what we're doing right now. We just did word problem. Now we're going to do these two blocks right here. How do we create a truth table, and how do we write a logic expression? Okay. So truth tables. A truth table we talked about before. It is a table where we hit all of the possible combinations for a particular set of inputs. Okay. And how do we know how many combinations there are? Our old friend 2 to the n, right? 2 to the n. So if there's one input, there's 2 possibilities. If there's 2 inputs, there's 4 possibilities. If there's 3 inputs, there's 8 possibilities. 4, 16 possibilities, and so forth and so on. Okay. So every kid, every time that we build a truth table, it starts off the same way. So let's say we have 2 inputs. All right, I'm going to call them input A and input B. Okay. You guys can see my piece of paper, right? Okay. And then output, whatever, I'm going to call it just Z, I guess, just because why not? And I'm going to draw a line there, a line here. I like to get in the habit of doing a double line between inputs and outputs, just because if we have lots of inputs, lots of outputs, maybe it's a little bit clearer that my inputs are over here and my outputs are over there. Now, I don't know anything about this circuit that we're trying to do here, but I don't need to start to build the truth table, because every truth table is built the same way. We go 0, 1, 0, 1. And then in this column, 0, 0, 1, 1. We alternated every 1 row, and then we alternated every 2 rows. Why did we do that? Well, first of all, it's a prescribed order. Does it really matter, like, as long as we get all the combinations, what order we put it into? You know, not really, but you as a teacher, please take my word for it. Force your kids to do it in this order. My first maybe 2 years, I was like, I'm laid back and hip. It's cool. Put them whatever order you want. No, don't do it. Trying to reverse this order or figure out what they've got is a nightmare. Plus, they forget combinations or they duplicate ones. So always this format. I teach them every time you're going to do a truth table, 0, 1, 0, 1, then 0, 0, 1, 1. That hits all the combinations. Side bonus, you have also just counted in binary. This is 0, 1, 2, and 3. You counted in the right order in binary. So not only did you make sure you hit every combination, but you're also in sequential order, which is pretty nice. Okay. So then we would dream up some circuit, and we'd say, okay, so in this circuit, whatever it's supposed to do, if A and B are 0, then the output is supposed to be 0. And if A is 0 and B is 1, then the output is supposed to be a 0. I'm just making this up, guys. This is not anything you should have figured out, okay? And then let's go ahead and put a 1 in this row. If A is 1 and B is 0, then the output would be a 1. And we'll make this one a 1 as well. So some word problem would tell us that when these conditions are true, we have a 0 output. If these conditions are true, we have a 1 output, whatever it is. It's irrelevant right now, but that's what it's supposed to be. So that's how we set up our truth table. We put our inputs, those are always the same, and then our outputs are defined by the circuit we're trying to make. Okay? That's a truth table. And then we go immediately to a logic expression. So here's how we do that. We basically say, in what conditions do I get a 1? In what conditions do I get a 1? So I look down my output column here and I say, oh, here's 1. How do I get a 1? Well, A has to be a 1 and B has to be a 0. So A is 1 and B is 0. Another way to say that would be A and not B. A and not B. And so what I'm going to do is I'm going to write that. A. Do you remember how I do and? Do you remember what and was? It was not addition. I'll give you a hint. We always think it's addition. What's and?
Multiplication.
Multiplication, right. I'm not going to put an X in there because it's going to get confusing. So I'm just going to write A and B right next to each other. That means they're multiplied. Oh, but it's not B, is it? It's that. A and not B. That's how we write that. A and not B. So that's one possibility. That's one way I can get a 1. But there's another way too. What would this be? Anybody got an idea of what this would be as this thing over here?
A and B.
A and B. A and B. Yep. Now these things we're writing over here, guys, are called min terms. Min terms. That's the vocab term for these things we're writing. They're called min terms. So that's it. Those are the two possibilities, two ways that we could get a 1. If A is 1 and B is 0, in other words, A and B not, or if A is 1 and B is 1, in other words, A and B. So now what we do is we say, okay, so this circuit is A and B not, or what was or? What mathematical term, what operator was or? That was a plus. That's or. A and B. That is my logic expression. That defines whatever word problem gave us this truth table. That's what this is. Now, the next step, which we're not going to get to today probably, well, maybe, is that this would go then into a circuit. Like you can take this and go directly into a circuit. That's the point. Okay, is that we can take these min terms, put them into this expression, and then we can take that right into a circuit. Questions so far? Okay, let's do a bigger one. Let's do just another one for practice.
So we are just identifying the conditions, right?
Yes.
by this?
Yep.
We are just defining the conditions right now.
Yep. Yep.
Okay.
Just defining what makes, in this circuit, what makes a 1.
So we're still far away from saying which is majority or.
Oh yeah. We're building the skill right now that we're going to need, a skill that
Okay.
we're going to need. But yeah, we're not even close to that yet.
Okay.
You got it. So let's do a 3 input now. Okay. So I'm going to pick, I can pick A, B, and C again. I tell the kids, if you have a word problem, these letters should probably be meaningful. Okay. But right now we don't really have a word problem. So I'm going to stick with A, B, and C as my inputs and Z as my output. Just stay kind of consistent there. All right, so I don't know anything about this problem, but my truth table, I already know how to make because I always make them the same. First column alternates 0, 1. Uh-oh, how many rows do I need to make? If you spaced out and don't know what I'm talking about and you need an answer, the answer is always 2 to the n, right?
That would be 9, right?
Almost. There's 3 inputs, so 2 to the third is how many rows there will be. So there would be 8. 8 rows. 0, 1. 0, 1. There's 4 rows. 0, 1. 0, 1. There's 8 rows. Next column over. Now I alternate every 2. 0, 0. 1, 1. 0, 0. 1, 1. Any guesses as to what goes into column A on that pattern?
4 zeros and then 4 ones.
4 zeros and then 4 ones. Holy cow, he's right. It's almost as though there's a pattern here. And one could describe that pattern, mathematically speaking, as 2 to the n. Here we alternate every 1. Here we alternate every 2. Here we alternate every 4. If we had another column, we'd alternate every 8. Now we know we've gotten all the combinations because we did it this way. And it also, side benefit, happens to be in perfect Boolean order. So it's 0, 1, 2, 2, 3, 4, 5, 6, 7. Side benefit. All right, so let me just throw a couple of randoms in here. I don't even know what I'm doing here. We'll go 1, 0, 1, 1, 0, 0, 0, 1. Again, the word problem would define what's in there. We don't have a word problem, so I'm just throwing some random stuff in there for right now. All right, so I'm gonna phone the audience here. I'm gonna ask you guys to contribute because I've been talking all night. I'm worn out here. So let's see. Sam, can you pull a min term for me? Can you tell me what one min term in this truth table would be?
I guess the easiest one would be row 7, ABC.
Right here?
Yeah.
He says ABC, so it's 1, 1, 1. So yeah, it would be A and B and C. Absolutely. Fair play. Okay, Jim, you're next on my Brady Bunch squares here. Jim, can you pull a min term here for me?
I was writing that one down.
Oh.
How about A, B, not C for row 6?
So, okay. So row 6 would be A, B, and then C not. That's you're right. That would be, except we're not going to pull that one because we have a 0 here.
Sorry. Yeah.
That's okay.
How about not A, B, C for row
Not
3?
A, B, C. So this row right here, not
Yeah.
A, B, C. Absolutely correct. By the way, I think I might have mentioned this last week. When you're in class, you got to be consistent about whether you say a not or not a. There's not, there isn't a right way or wrong way, really, but be consistent. Because if you say a not b, was that, or was that this, right? Was that a not b, or was it a not b? So you just got to kind of be consistent and clear with your kids as you're working. Okay, so let's see. Andy's next on my list there. Andy, can you pull another midterm?
Not A, not B, not C.
Not A, not B, not C. So that would be this very first row. Not A, not B, not C. Yep, not A, not B, not C. Sure. Phil is next on my list here. Phil, maybe one more. Can you do one more midterm?
So let's see, that's a 1. So for row 2,
Right here?
yeah, not A, B, not C.
Not A, because it's a 0. B, because it's a 1. And not C, because it's a 0. Yep. Looks good. So I have 4 other rows here that we're not doing because they're all zeros. The midterms are just saying, how would I get a 1? Now I'm almost done. I got midterms, but I'm not done. I need to put it into an expression. That's the last step. Okay, so I'd say Z equals, and I just grab all 4 of these midterms. So A not, B not, C not, or A not, B, C not, or A not, B, C, or I ran out of room on my page. A, B, C. Okay. Questions about that? I'm going to do one more.
Okay,
do one
question,
Yes.
Michael.
Yes, sir.
So the only min terms are the ones where the output is 1, is it?
Correct. Correct.
Okay.
I got a quick question.
Yeah.
So when you're going over this for your class, is this how you actually teach truth tables, by hand drawing and such like this, instead of doing the PowerPoint of this activity?
Yeah, the PowerPoint's fine. I just find when I do it, maybe it's just my kids, when I just like click and it shows up on the screen, they're like, yeah, okay. And they don't practice like writing them out. And then that's when I get all sorts of like wacky order and they miss ones or whatever. If they actually walk them through like alternating the numbers, that's when they tend to master it pretty well. So nothing wrong with, by the way, though, you could put up on the projector and be like, and now you copy it into your notes. Do it right now. You could do that too. Okay. So big money, big prizes here. We're building our skill. We're going to do a 4-input truth table. A 4-input truth table. So we need lots of space here. 4-input truth table. So 2 to the n, 2 to the 4th power. I'm going to have 16 rows here. Lots and lots of rows. And this time I'm going to specify, I'm going to pick some different letters. So this time I'm going to pick the following letters up top here. I'm going to pick P, V, S, and T. Those are the letters I'm going to choose right now. I recommend you also choose those letters. Wink, wink. Okay. And then I have my outcome, my output. This time I'm going to call that O. If you add like, like an alarm or a light or a buzzer, then you might use different letters for the output to to suggest what that is. All right, I'm not going to draw my lines yet because I'm going to make sure I'm trying to stay neat here. And I'm going to draw my numbers first. All right, so I have 16 rows. But knowing nothing about this circuit, I still know how to make the truth table. It's going to be 16 alternating zeros and ones. 0, 1, there's 2. 0, 1, there's 4. 0, 1, 6. 0, 1, 8. I'm halfway there. 0, 1, 10. 0, 1, 12. 0, 1, 14. 0, 1, 16. Did it. Whew. Next column over. Now I alternate every 2. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Next column over, now I'm alternating every 4. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Finally, the fourth column. We mentioned this last time. Now we have 8 zeros and then 8 ones. So 0, 0, 0, 0, 0, 0, 0, 0. There's 8 of them. And then 1, 1, 1, 1, 1, 1, 1, 1. Whew. That was a lot of work. Use a circuit board for a straight edge for extra nerd points. All right. Now, if you haven't picked it up already, these letters stand for president, vice president, secretary, and treasurer. You have just laid out your truth table for majority vote. This, by the way, Ryan, is not something I would do with my students. I'd make them do more practice before we jumped into this. But you guys are on a truncated timetable, so this is your majority vote truth table, or the beginnings of it anyway. Now we actually have a word problem. Now we actually do know what to put in this output column because we have a word problem. Okay, so so the vote passes, meaning we get a 1 when the majority votes yes, votes 1. So anytime where I have 3 ones, I know this output should be a 1. So I'm going to start with those because they're easy. So here, all 4 people voted yes. Well, that's obviously a yes. That's a pass. Here, 3 out of the 4 vote yes. So that's a yes. Here, 3 out of the 4 vote yes. So that's a yes. I'm going to come back to this one because this is a tie. So I'm going to come back to that one. 3 out of the 4 here. That's a tie. That's a tie. And then, okay, 3 out of the 4 here. All right. Now let's go deal with our ties. So president and vice president vote yes. This isn't focusing very well. There we go. President and vice president vote yes. Secretary and treasurer vote no. Does the vote pass? Yes, it does, because it was a tie, but the president voted yes. So, yep, that's a pass. Here we've got the president and the secretary vote yes. The other 2 vote no. Does it pass? Yep, because the president voted yes. Here, the president and the treasurer vote yes. Everybody else votes no. That's a pass. Yep, that's a pass. Here, the president votes yes. Everybody else votes no. Does that pass? This is what I call the dictator row, right? This is the fascism row right here. So no. President votes yes. Everybody else votes no. The vote does not pass. Okay, and then just working our way backward here. So president votes no. Treasurer votes no. Vice president and secretary vote yes. So it's a tie, but the president voted no. So that doesn't pass. Same thing here. It's a tie, but the president voted no. Here, the poor vice president was the lone voice of affirmation here. Vice president votes yes. Everybody else votes no. That's a no. Here we have a tie, but the president voted no. So that's a no. Secretary voted by himself. Nope. Treasurer voted by itself. Nope. And everybody voting no. That's a pretty obvious no. Questions about how I set up this truth table before I start talking midterms? All right, so on big truth tables like this, I like to count the number of ones because that tells me how many midterms I'm going to have. It's like kind of a mental check for me. I'm going to see how many ones I have, and that's how many midterms I should end up with. And that way, if I count my midterms at the end and I have too many or too little, I'm like, oh, I made a mistake. So real quick, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 ones. So I should have 8 midterms. Okay, so where did I leave off? I think I left off with Ralph. Ralph, let's try and stay in order top to bottom, everybody. Ralph, can you tell me what the first midterm would be? Count from top.
Not P, V, S, T.
Not P. So we're right here because it's a 1. Not P, V, S, T. Is that what you said?
Yes.
Perfect. Yep, that's good. Wayne, how about you? What would be my next midterm?
So it would be P, not V, not S, and T.
Very good. 1001, P, not V, not S, T. Okay. Ryan, how about you?
The next one should be P, not V, S, not T.
P, not V, S, not T. Yep, I like it. Alfredo, you still? Oh yeah, he's there. I thought you left. I see you. Alfredo, what's my next one?
Okay, the next one is P, not B, S, T.
Very good. 1011, P, not V, S, T. Sure. Harish, what would the next one be?
That would be P, V, not S, not T.
Very good. Very good. Okay. Jess, how about you?
That would be P, V, not S, T.
Very good. You guys are nailing this. All right, Murat, how about you?
Okay, PV, S, not T.
Very good. And see, Skylar, connecting to audio. You probably can't hear me right now. We'll come back to him. How about Chris? Chris. Busted. Jacob, you out there in the ether?
Yep.
Jacob, what would the last midterm be, buddy?
PVST.
All right. PVST. All ones, so no knots over here. So now I just count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. I had 8 ones. I have 8 midterms. That all matches up. You guys as teachers, when you're checking this, that's a super quick check because it's so easy for kids to miss these. And so they'll go write it in their expression now. So, okay, so outcome is, and they're going to write these 8 midterms. P not V S T, or P V not S not T, or et cetera, et cetera. And it's so easy to miss one, right? Or to duplicate one or whatever. So checking this as they go is pretty critical. At this stage, they get all 8 of these written out. I'm being a little lazy here, but they get all 8 of them written out. I say, all right, give this to a partner, hand it to your partner or somebody in the class, and have them just double check. All right, double check yours with theirs. Make sure you guys are on the same page. You guys are doing the same circuit, so it should basically be the same. Helps catch some of those, little, minor errors that turn into major ones later. Okay, an error in the design stage is going to cascade through the rest of the problem. I can't tell you how many times I've had kids in the more complex circuits, like the date of birth circuits, like the big bad, right? It's the end of unit 2, where they're like breadboarding. And I'm like, hey, this worked in simulation, right? And they're like, well, I didn't test it. I'm like, what? And I'm like, well, let's go back and look at the design. And like, literally it was wrong here. And so it was wrong here. And so it was wrong in the simplification. It was wrong in the, circuit design. It was wrong on the breadboard. So making sure that they're checking along the way goes a long way. All right. So at this point, you could be working on the activities 126 and 127, random number generator that we did earlier tonight. You're going to be looking at 211, which is the activity truth tables to logic expressions. It's just some practice going through these truth tables. To be honest with you, if you're feeling comfortable, which some of you seems like you are, you don't have to do every single one in the lead up, because that's kind of what we were doing here together. But after they do like here's the basics, then they actually have you do some kind of interesting, word problems and things like that. They have this one about grandma and her cats and pollen detector and stuff, which is kind of interesting, the humidity. And anyway, so that's really what I think would be more valuable to you, is kind of looking at those things towards the end of the assignment. Okay. So that's 211. Now, also, you now have the ability to do the design brief for majority vote, which hopefully you did with me. The truth table for majority vote, which you have here. You probably want to copy it into wherever you're going to have your documentation for majority vote. And you can pull the unsimplified logic expression for majority vote. So you can do all those steps as well, so that you're not just slammed with majority vote all at once. Okay, just kind of hitting it as you go, taking off little bites as you go. All right. On Thursday, we're going to jump to turning this into a circuit. I got to see what Thursday is. Oh man, Thursday's a big day. So yeah, so turning this into a circuit, and then Boolean simplification. So we're going to use Boolean algebra, which is kind of like algebra, but different. Okay. It's a lot like algebra, but different, just different enough to be frustrating. And that'll help us take this big, nasty circuit down to something significantly smaller. And some of your kids might see it in here. Like, for example, if the president and the vice president and the secretary and president, vice president, and secretary, if they all vote yes, do we care what the treasurer voted? We don't. And I don't mean that in a mean way. I just mean it doesn't matter. If these 3 vote yes, the vote is passing. Right? And so some of your kids kind of might start to pick up maybe intuitively, maybe we don't need both of these conditions. Maybe we don't need both of these midterms. Right? If I said, for example, P and V and S, that is kind of both of these rows. Right? And so some of your kids might like start to start to broach the topic of that simplification. You say, hold on, you're feeling it and that's good, but there's a process for us to do this. What you don't want kids to do is start to be guessing this, what would simplify, because number one, they're going to guess wrong. And number two, they're not going to guess like all the way down. Okay. We're going to show them a process to take this all the way out to the most simple form. Okay. So that's kind of our next step. Questions?
So Michael, this means that you're looking for redundancy in this?
We will be.
So those that are redundant, they can be clubbed together, or
Yep.
we do only one instead of the both, right?
Yep. That's what Thursday is going to be about, is how do we find those redundancies and get rid of them?
Okay.
Okay, cool. This is a big moment. Like right at this moment, they can take a word problem, put it in a truth table, take the truth table, put it into the expression. With Thursday in the first hour, they're going to learn how to turn this into a circuit. And that's like, boom, doors open. Now you can go word problem to circuit. So I can describe a circuit to you and you can be like, yeah, I can do that. Truth table, logic expression, circuit. That's huge. I always love, like I told you
here, Michael, O means just the output, right?
Yeah, O is the
So
output.
we're not talking about, okay. So we write it out and then cross out the redundancy here.
No, don't cross out any redundancy.
We don't.
No, leave everything as it is right now.
We leave it as it is. Okay.
Yeah. I know you're chomping at the bit. I know you want to, but you gotta wait. Okay, so that's all I've got for you this evening. I will stick around for an hour, work through your stuff. Let me know if you need help, because that's what I'm here for. And yeah, and let's double check the, before I let you go, let's double check the, it's your turn. Make sure there's no surprises or things that are unclear there. Close. Go back. Nope, I need block 5. We're in block 5. It's your turn. All right, so they ask you to work through 126 and 127. And then right here, this is what's going to go on the submission form. You're going to take your 555 timer from 126. You're going to take your big sequential combinational logic from 127, and in one multisim file, you're going to have the whole random number generator circuit from beginning to end, so you can actually see it work. That's what'll go on your submission form. Okay, and then you're going to work on 211 and submit a screenshot of your progress there. You're not right now submitting majority vote, but you will. So I would recommend that, on a separate piece of paper or whatever, you're putting the steps, the design brief and the truth table and the unsimplified logic expression for majority vote so far. You're not turning it in before Thursday or anything. I'm just saying that would be, while it's fresh in your brain, it would be a good thing to do. This is the area in 211 I was saying that, you guys are probably fine with. Double check, make sure you're feeling good. But right here at maybe step 9, this is where the meat really comes into it. I like this humidity sensor 11 and 12 here. There's some good stuff in there. So that's really what I'd be looking for. 9, 10, 11, 12. Okay. All right. Well, have a wonderful evening, everybody. And I'll stick around if anybody needs me.
Good night.